Okay, so now we're going to look at correlation. And once again, we're going to be looking at matched pairs of data. So, for instance, we'll have um, one ordered pair, and that would be one value of our data set. Then we'd have another ordered pair, and that would be a second value in our data set. And we would continue on in this fashion. We continue on in this very fashion until we have n ordered pairs in our data set. So we are looking at ordered pairs. We're actually looking at n of them. And what we're going to be doing is we're going to be looking to see if there is a correlation between the first and second coordinates of these ordered pairs. And of course, a correlation exists between two variables, let's say x and y, when the values of one variable are somehow associated with the values of the other variable. Now, if you take a look at these scatter plots here, we have here a bunch of ordered pairs. This is however many ordered pairs we have here, that would be the number n, or the number of data values. And here would be the y-axis, here would be the x-axis, and each one of these points comes from graphing the x value and the corresponding y value as ordered pairs in the rectangular coordinate system. So these are all just rectangular coordinates. We have y-axis and x-axis for all. And as you see, in some cases, the x values and the y values have some kind of relationship. For instance, in this first one here, for A, as x increases, as x gets larger and larger and larger from left to right, y is also getting larger and larger. So as you see down here, for the smaller values of x, the values of y are also small. And for the larger values of x, the values of y are also large. As a matter of fact, if you wanted to, you could actually draw a line um, that could kind of be, oops, that line is too light, but you could draw a line that could kind of be a prediction line, or some kind of line um, that would be a model for this data set. And that line would kind of show you that this data set has an increasing slope that would uh, be a positive correlation, because as x increases, so does y. And if you do the same thing over here, draw a line to kind of model it, you see here that as x increases, as x gets larger and larger and larger, y actually decreases. So as x increases from left to right, y actually starts very large when x is very small. And as x gets larger and larger and larger, y gets smaller and smaller and smaller. So that would be a negative correlation. Here, there doesn't seem to be any correlation at all. As x increases, you still get small values of y, but you also get large values of y. And when x is very small, you have small values of y and large values of y as well. So there seems to be no correlation here. And here, there seems to be a correlation, but the correlation here doesn't seem to be that of a line. In this case, the correlation would seem to be like a parabola, kind of. This would be what I would call a quadratic correlation. So here we have two linear correlations, one with a positive and one with a negative slope. Here's the positive slope correlation. Here's the one with the negative slope, a negative correlation. And this would be more of a quadratic correlation, a parabola. Now, in general, or sorry, in this course, we're only going to be looking at the linear correlations. So we're only going to be looking at ordered pairs that can be modeled by straight lines. So the first thing we're going to define is we're going to define the linear correlation coefficient. And you've been looking at some linear correlation coefficients up here. R is the linear correlation coefficient. The linear correlation coefficient R measures the strength of the linear correlation between paired quantitative x and y values in a sample. So for instance, this linear correlation, the strength of this linear correlation is 0.851. and the strength of this linear correlation is negative. Notice it's negative because there's a negative correlation. As x gets larger, y gets smaller. Negative 0.965. Here the correlation is zero, no correlation. And here the correlation is negative 0.087. That's very small. That's a very small number. Very close to zero, very close to no correlation. And that's because there is a correlation here, but it's not linear. So this correlation, this linear correlation coefficient measures the strength of the linear correlation and only the linear correlation. There is some correlation here, but it's not linear, so that's why the linear correlation here would be deemed to be very weak. But this is the Pearson product moment correlation coefficient. This is R, the Pearson correlation coefficient. Now, R squared, if you take R and you square it, for instance, if you take this value and square it, or this value and square it, or one of these values of R and square it, then you get another statistic, and that is R squared, and it is the proportion of variation in Y, the dependent variable, that is explained by a linear relationship between X and Y. So it's how good the model would be if we made a linear model, basically. That's what R squared tells us. Now, we're going to look at calculating R in two ways. One way is by using one of these formulas right here, and you can see these formulas are very complicated. The first formula here, 10(1), says we would take the number of data values and multiply it by the sum of the product of the x and y values. So we'd multiply all the x and y values first, and then we'd add up all of those numbers, and then multiply that answer by the number of ordered pairs. Here we have adding up all the x values, adding up all the y values, and then multiplying that answer, and we'd have to do the subtraction of those two numbers as the numerator. In the denominator, we have two square roots, two radicals. Under one square root, we have the sum of the x's squared. So we have to square all the x's and add them all up, square all the independent variable, add them all up, and multiply that answer by n. And then we'd sum up all the x's, that same factor here, the sum of the x's, but we'd square that number, and then we'd subtract and take the square root. And here we do the same thing for the y's. But that's quite time consuming and tedious. And even this formula, 10(2), which is a shortcut, even with this formula, we have to calculate the z-score for all the x and y values. We have to calculate the z-score for every x and y value. So we'd have to calculate the averages and the standard deviations, then calculate the z-scores, and then we have to multiply all those together, and then we have to add them all up and divide by n-1. That's the shortcut formula. We're not going to use either one of those formulas, but those are the formulas if you want to calculate this. If you want to actually find these numbers, those are the formulas. What we're going to do is we're going to use a little bit of technology, and we're going to use the technology in lieu of these formulas to calculate the correlation coefficient for this data set. Now, these ordered pairs represent CO2 levels and temperatures. Let's see. Concerns about global warming have led to studies of relationship between global temperature and the concentration of carbon dioxide. Listed below are concentrations in parts per million of CO2 and temperature in degrees Celsius for different years based on data from the Earth Policy Institute. Is there a linear correlation between temperature and concentration of CO2? Well, let's see. Let's calculate the correlation coefficient here. Let's bring out our TI-83. So we bring out the TI-83, turn it on. And what we're going to do is we're going to go to Stats, we're going to go to Edit, and we're going to edit our list so that L1 contains the CO2 levels. So you see the CO2 levels are all here in L1. So this one contains all 10 CO2 levels. And L2 contains all 10 temperatures. So we put our match pairs into list 1 and list 2. So 3, 14, 13.9, we put them in the correct order. So in list 1 we have the first CO2 temperature as the first data value, and in list 2 we have the first temperature as the first value. So they are in order, and what we're going to do is we're going to go second quit to get back to the home screen. Then we're going to go back to stat, and we're going to go all the way over to test, Now there's a test down here called the lin-reg test. And lin-reg test is E. So we're going to go to lin-reg test, we're going to press enter. And it's going to ask us where our X list is. That's the list that we want to be the independent variable. So we want to use the CO2 levels as the independent variable. So we're going to say list 1, we're going to keep that the same. And the temperatures we're going to look at as the dependent variable. So we're saying here that we're going to try to see if the uh, if the temperature is linearly correlated to the CO2 levels. And let's see, the frequency is 1. And then it's going to ask us for the alternative hypothesis. Well, what we're going to do is we're just going to keep that as not equal to. And we're going to explain all that when we get to the hypothesis testing part. We're going to keep that as not equal to for now. And you can do that if you're just trying to calculate R. And then it asks regression equation. We're going to ignore that also. And we're just going to go to calculate and press enter. So all we have to do is tell it where the lists are. List 1, list 2, the frequency is okay. And leaving this as not equal to is also okay. And then we go to calculate and we press enter. And we see a bunch of information here. And we're going to use actually that information when we do the hypothesis test. But right now, what we're concerned with is this value of R. So this is the value of the Pearson correlation coefficient R, 0.892. So for our data set here, let's see, R is equal to 0.892. All right, so that's how we're going to calculate R. We're not going to use either one of these formulas. We're actually going to calculate R using technology, using the TI-83 calculator. And let's scroll down here and see how we're going to interpret R. Okay, so there are two ways we're going to interpret R. Now, we can either use the value of R, or we can convert R to a T test statistic and do the test for R there. So we're going to have two interpretations of R, okay? And this little chart is going to show us how to interpret R. Table A6. Uh, so we're either going to use table A6 to interpret R, and if the absolute value of R, denoted this way, the absolute value of R, exceeds the value in table A6, conclude that there is a linear relationship. Otherwise, there is not sufficient evidence to support the conclusion of a linear relationship. So we're going to take our value of R, and we're going to use table A6. Let's see, N is the number of matched pairs. The number of matched pairs is 10. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 ordered pairs. So we're going to look for N, and then we're going to look at the critical value. So if we look down here, N is 10, and we're going to look at the critical value. Well, the critical value depends on our significance level of alpha. But if you take a look, our value of R, 0.892, actually exceeds the critical value regardless of which significance level we're using. 0.892 is bigger than 0.632 and also bigger than 0.765. And right here it says if the absolute value of R, which is 0.892, exceeds the value in the table, which it does, conclude that there is a linear correlation. So we can conclude here that there is a linear correlation. That is how we would use R in order to see if there is or is not a linear correlation. Now here's how we'd use software, interpreting R from software. So let's say we don't have table A6 handy, but we do have handy our TI-83 calculator. Okay? And from the TI-83, if you look, when we did that lin-reg test, one of the numbers that was given to us was the p-value. See? It gave us the value of R down here, and R squared as a matter of fact, but it also gave us the p-value. And here it says if the p-value computed from R is less than or equal to the significance level, conclude that there is a linear correlation. Otherwise, there is not sufficient evidence to support linear correlation. The p-value here is 0.0005. So this scientific notation, that's 5.2193335 times 10 to the negative fourth power. If you convert that to standard notation, that's 0.0005 if you round it. So the p-value here, the p-value is 0.0005. And it says here that if the p-value is less than or equal to the significance level, well, this is less than a significance level of 0.05, and it's less than a significance level of 0.01. So it is going to be less than the significance level that we would normally use. So we can conclude that there is a linear correlation between the observed, between the x and the y values here. So as you can see, we can use either technology or we can use table A6 to determine use R to determine if there is a linear correlation between the X values and the Y values of our data set.